Hi there, this is Ms. Page. In this lesson, we are going to learn how to evaluate inverse trigonometric functions. So in our prior knowledge, we have done problems like these here, where we are to find values of x over the interval from 0 to 2 pi, 0 included, 2 pi not. So here we have sine of x equals 1/2. So when we look at this, we know that x would be an angle, perhaps like a theta, all right? But it's an angle type of situation. So we know that that's an angle. So we're looking for values of angles. And the angles in our first positive revolution that have a sine of 1/2 are pi 6 and 5 pi 6 in quadrants 1 and 2. Here we have cosine of angle x equals -1/2. And in our first positive revolution, the angles that have that cosine value are 2 pi thirds and 4 pi thirds, which would be quadrants 2 and 3, where cosine is negative. So when we look at inverse functions, we have to make sure that for problems, when we're doing inverses, and this is where our prior knowledge is related, we have an inverse function where our angle becomes our y value and our sine or cosine value becomes our x. So these become our x's and our angles become our y's. Because as we know in inverse functions, domain and range switch places. So here where x was angle, it will become our range of y. Here where x or the y was 1/2 the value, it will become our domain of x. And in an inverse, if we want it to be a function, we have to make sure that it's a 1-to-1 correspondence. All functions are 1x, 1y. And the problem with sine and cosine, and also so they're inverses, but here sine and cosine, is that when we invert them, they are not 1-to-ones because of their periodic nature. So there's something called the horizontal line test. The horizontal line test is a test of a function that determines whether its inverse will also be a function. So if on the horizontal line test, we draw a horizontal line here, that horizontal line is shown here by this red line. If it intersects the function at no more than 1 point anywhere on the function left or right, then its inverse will be a function. And if it intersects more than once, then the inverse won't be a function. And so for the horizontal line test, for this is our sine curve, it intersects more than once. And that means the inverse won't be a function. So we really want an inverse function. So that means we're going to have to restrict the inverse functions situation so that we're only dealing with a portion of the sine curve. So for sine, what we do is we look at our first quadrant in which sine is positive and our fourth quadrant in which sine is negative, and of course 0 as well. And that's actually going to give us then, notice, a 1-to-1, because in this section, horizontal lines only intersect the function at 1 point. That's what we're going to take a look at here next. So here's our inverse sine function. So for the inverse sine function, two ways that we can write the inverse sine function with our superscript notation of -1. Notice the position of it. It's like where we put an exponent. Remember, this isn't an exponent. It means inverse. There's another notation, an arc notation here shown. So we can also write it with arc as a prefix of sine. And that means we're dealing with the inverse function. So remember, in an inverse, domain and range have switched. So what follows our sine here, our arc sine and our sine inverse, these right here are sine ratios. So those are your sine ratios or values. And your y now are your angles. So what we do here, that's what this is saying. The angles are y or f of x. So one of the things we learned previously is that sine's maximum value is +1 and its minimum value is -1. So that now becomes its domain because these are the sine values, our x's. And that's what we're looking at here. Here's our x-axis. So our domain goes from -1 to +1. That's our domain. Our range, we're looking at our range, which is now our angles. And to make sure that we have a one-to-one relationship to make our inverse a function, we're going to restrict our angles to be in our first and our fourth quadrant. But we want them to be next to each other. So for the fourth quadrant, we have to use negative angles from 0 to -π/2 here. So this represents our fourth quadrant values where sine is negative. And this represents our first quadrant angles in which sine is positive. That way we get all of the sine ratios and one angle answer for each of those sine values. Similarly for cosine, here's our cosine. So similarly for cosine, or inverse cosine function, so we have cosine inverse of x or arc cosine. Our angles are the y values. So again, we have that reverse relationship. So our f of x or y values are the angles. And these x's are the cosine ratios. So cosine, again, remembered, like sine and cosine have the same maximum of 1 and the same minimum value of -1. So that becomes our domain from -1 to +1 inclusive. Now for cosine, the way we have to restrict cosine to make sure that we're contiguous with our angles is we take our first quadrant where cosine is positive and we take our second quadrant where cosine is negative because x is negative in the second quadrant, and that's, remember, a cosine value looking at the unit circle notation. So that's what we're looking at here. So here's our domain from -1 to +1. That's our domain for our cosine. This is our x-axis. And with our y-axis, notice these are our angle values. So here we're dealing with this right here from π/2 to pi. That is our second quadrant where cosine is negative. And here is our first quadrant from 0 to π/2 where cosine is positive. All right, one more to look at. That's our tangent function. Here's our inverse tangent. Inverse tangent. Again, we have the two notations with our superscript of -1 or arc prefix. So remember that, again, y will be our angles now because domain and range have switched for our inverse function, and x is our tangent ratios. Tangent, if you recall from when we graphed these functions, the domain for tangent is restricted in that you have undefined ratios or undefined situations. So our angles now are going to be our y values. So we're looking at our range being restricted. The value of tangent has no maximum and it has no minimum. The tangent ratios, there's no maximum, no minimum, which means that it goes from -infinity to +infinity. That is now our domain. And our angles, in order to make our inverse a 1-to-1 ratio, so it's a function, we again restrict to the first quadrant and the fourth quadrant. But this time, we leave out the angle values of negative pi halves and positive pi halves because at those, our tangent is undefined. So our tangent of our angle of pi halves, that's sine of pi halves over cosine of pi halves, and that is equal to 1 over 0, which is undefined. So we don't include pi halves because it's undefined. Tangent's not defined there. And for negative pi halves, sine is -1 and cosine is again 0. So it's undefined there also. So that's why you see these don't have the equals portions like they did with sine. If we look back at sine, notice we have less than or equal to pi halves. The negative pi halves is less than or equal to our angle values. But for tangent, we do not because tangent is undefined at these two angles. So when we invert it, we get this right here. So this is our x-axis. Notice that it goes to the left and the right to infinity. So that's from our negative infinity to infinity. That's our domain. And then our range, we restrict to, here is our first quadrant where tangent will be positive. That's quadrant 1 where tangent is positive. And then we have our fourth quadrant. Again, we use those negative angles to make our two sections contiguous on the number line. So this is where our tangent is negative, which is quadrant 4 in this case, from 0 to negative pi halves. All right, so now we're going to put that to work. So here we are going to, if possible, find each exact value of these given expressions. So let's take a look at this first one here. Arcsine of -1/2. What we have to realize when we're looking at this, because of the arc prefix, the -1/2 is our sine ratio. So we're looking for an angle. And you can use, angles are y's, you can also just use theta if you want to. I'm going to use y as the notation. So y, which is an angle, I'm looking for the angle that has a sine of -1/2. And what I have to realize is that in previous, when we did our unit circle and we were solving our trig equations, we would have more than one angle. Here we should have only one angle answer at the most. So we have to be aware of our angle restrictions for our inverse sine function. And that means we have to know that our interval for restrictions are here. Quadrant 4 with negative angles in quadrant 1. So sine is negative in quadrant 4. So we're looking at this portion right here. So then we need to realize that, well, what we normally would have called 11 pi 6 as our angle answer, we need its coterminal angle in the quadrant 4 as a negative angle, which would be negative pi 6. All right, so that's what this would be equal to, negative pi 6. Here, what we're looking at for the second one, so here we have cosine inverse, because we've got this superscript of -1 here. So we're looking for, again, y equals what, and y is an angle that has this cosine ratio of -√2/2. So what we should know is our √2/2, positive and negative, go with our fourths for both sine and cosine. Here we're looking at cosine, which is our x. So we need to realize, all right, for cosine, our angles are restricted to the first and the second quadrant. So we're going from 0 to pi. And where cosine is negative is second quadrant. And that would make this one 3 pi 4ths. And we don't have to worry about the conversion or thinking in terms of negatives for cosine. So in many ways, that makes cosine a little bit easier. Looking at our third one here. So again, we have an inverse function. Here is sine inverse of 2. So here again, we'd be looking for an angle in which our sine ratio would be 2. So we have to remember here that our domain for our sine function here is our ratios. This is our domain, our x's, that it only goes to positive 1. It does not get any larger than that. So there is no way that we should have a value, a sine value of 2, which means that this one is not possible, or you can say it doesn't exist. But it said, if possible, find the exact value, so I'm just going to say that one's not possible. All right, moving on. A couple more here. These are both inverse tangent. So this one right here for tangent inverse of 1. So again, we have to realize that we're looking for an angle. And that 1 is our tangent ratio. So here we know that our tangent needs to be positive 1, and that we're looking at angles being restricted for tangent, again, to the first and the fourth quadrant, not inclusive of the negative pi halves and the pi halves, because that's where tangent is undefined. So one of the things that's very helpful is to know that this tangent of 1, this tangent ratio of 1, came from a ratio of sine and cosine, where sine and cosine had to have the same values, because only something divided by itself is equal to 1. So that happens, of course, at fourths. And so positive pi fourths is what I'd be looking at here, because the sine of pi fourths and the cosine of pi fourths are the same. They're both root 2 over 2, and anything divided by itself is 1. So that gives me pi fourths as my angle there. For this one, I have an inverse tangent function because of the prefix arc. So again, my angle restriction same as the previous problem. So now I'm looking for a tangent ratio that's negative root 3 over 3. Tangent is negative in the fourth quadrant, so I'm now looking at this right here. And so I'm looking for an angle where the sine cosine ratio is going to give me negative root 3 over 3. So I'm looking for sine over cosine. That's going to simplify really to negative 1 over root 3, which rationalizes to this. And that's going to happen if my sine is negative 1/2 and my cosine is root 3 over 2. Because in this case, the 2's would reduce or cancel, giving me negative 1 over root 3, which becomes negative root 3 over 3 as my tangent ratio. So what angle has a sine of negative 1/2 and a cosine of positive root 3 over 2? Well, in the first positive revolution, that's 11 pi 6. But again, that's not the angle we use here because we're dealing with our negative angle measurement. So we have to realize that 11 pi 6 is equivalent to negative 1 pi 6, or just negative pi 6. So that becomes our angle there. All right, so here we have some practice problems. Pause your video now. Do all of the problems and then come back. We'll go over them all at the same time. Let's take a look at the results. All right, so here we're looking at, we have arc cosine of negative 1/2, and so we are looking for an angle that has that cosine value. We have to realize that cosine would be negative in the second quadrant, and the angle that has that cosine of negative 1/2 would be 2 pi thirds. Here we're doing sine inverse of root 2 over 2. So sine is positive in quadrant 1, and the angle that has a sine of root 2 over 2 is pi fourths radians. Here we have cosine inverse of 0. So we have a cosine value of 0. Remember, values for sine and cosine of 0, 1, and negative 1 occur at the quadrantal angles. So we're looking only for the quadrantal angle in the defined angle interval for cosine inverse, which is from, remember, our 0 to pi. So we only use pi halves radians. You would not include 3 pi halves radians. In the next one, we're here looking at arcsine of negative root 2 over 2. So sine is negative here in quadrant 4. And the angle you might have been thinking about, which would be 7 pi fourths, we can't use that one because it's not in the defined interval for sine angles for the inverse function. We have to use its coterminal angle that's negative of negative pi fourths. Here we have arctan of negative 1. So we have a tangent ratio of negative 1. Remember, that occurs when sine and cosine have opposite values, and they have opposite values at our 3 pi fourths and our 7 pi fourths in our first positive revolution. But again, for tangent, our angles are defined as being from negative pi halves to positive pi halves. And so we can't use 7 pi fourths would have been the positive coterminal angle, but we can't use that. We have to use its coterminal negative value of negative pi fourths. Here we have tangent inverse of 0, so our tangent ratio there is 0. So we're looking for an angle that has a tangent of 0. That means that the sine has to be 0 because tangent is sine over cosine, and 0 divided by anything is 0. So we need to know, well, where is sine 0 basically within, again, the interval from negative pi halves to pi halves, and that actually happens at 0 radians where sine is 0 and cosine is 1. And so remember, that 0 here would be radians. This one is just a number. That one is an angle. All right, moving on. In these problems, they're a little more complex, involving our inverse trig functions, but also often we're looking at involving a sine, cosine, or tangent function as well. So for example, looking here at this problem, here we have arcsine of sine of 3 pi halves. So order of operations says we want to do what's inside our parentheses first. Here, 3 pi halves, we have to realize that's an angle. So we're looking at sine of an angle, not inverse. So sine of an angle, so we need to know what is the ratio or value of sine at the angle of 3 pi halves radians. So we have to use our unit circle knowledge. That would be negative 1. So now I have arcsine of negative 1. So now I have to realize, okay, now I'm looking for an angle because I have an inverse trig function here, inverse sine function. And angles for sine are again restricted to the first and the fourth quadrants. And I want to know what sine is negative in my fourth quadrant. Sine is negative 1 at the quadrantal angle of negative pi halves. That's equivalent to our 3 pi halves, but we have to use negative pi halves because of how our inverse trig function is defined. Let's take a look at this next one here. So here we have the cosine of the cosine inverse of negative 1. So again, order of operations says we do what's inside our parentheses first, and that's an inverse cosine problem. So here we would be looking to understand that that negative 1 right there, that's a cosine value or ratio, and we are looking for an angle. So we need to know what is the angle that has a cosine value of negative 1 where cosine inverse is defined, which is, remember, your first and your second quadrants. So for cosine, we're looking at going from 0 to pi. Cosine is negative 1 at the quadrantal angle of pi. So now what we have is the cosine of pi. So now we're doing like a unit circle problem. What is the cosine value of pi? And that is equal to negative 1. So the final value here is negative 1. All right, let's take a look at what's next. A couple more of these types of problems. So here we'll look at this one. This is a mixture of an arcsine and a cosine. So we have arcsine of cosine of pi thirds. So again, we do what's in parentheses first. So there we'd be looking for the cosine value of the angle pi thirds radians. So at pi thirds radians, our cosine value is 1/2. So that is now 1/2, and we have our arcsine out here. Arcsine, which is a sine inverse notation, that tells us we're now looking for an angle, and angles for arcsine are restricted to being from negative pi halves to positive pi halves. So 1/2 is our sine ratio. We want to know then what's the angle that has a sine value of positive 1/2, which would happen in our first quadrant, and that would be our pi 6 radians. And so that is what we're equal to there. For this one right here, we've got tangent of sine inverse of negative 1/2. So again, doing what's inside our parentheses first. If we're doing an inverse trig function, we're looking for an angle. And for sine inverse, again, we're looking at negative pi halves to positive pi halves, first and fourth quadrants. So this time, though, our sine ratio is negative, and so we need to know what angle would be this fourth quadrant, and the angle where sine is negative 1/2 in that quadrant would be our negative pi 6. So this becomes negative pi 6. And we have now tangent of negative pi 6. So now we use our quotient ratio for tangent. So this would be the sine of negative pi 6 over the cosine of negative pi 6. If you need to, you can of course change your negative pi 6 into its coterminal angle of 11 pi 6, if that makes the problem a little bit easier. However, that should still be sine. And then sine of 11 pi 6 is negative 1/2. Cosine of 11 pi 6 is positive root 3 over 2. This then reduces to negative 1 over root 3, which rationalizes to negative root 3 over 3. So that is what our expression is equal to. All right. So I have a couple of practice problems here for you to try. Pause your video and do them both. And when you come back, we'll go over both of the results. All right, let's take a look. Okay, so for this one, doing our cosine of 5 pi thirds radians first, that has a value of 1/2. And then looking for the angle, for cosine, angles are restricted to between 0 and pi, first and second quadrant. Where cosine is positive is your first quadrant. So where cosine has 1/2 as a ratio is pi thirds radians. For this one over here, doing our sine inverse of negative 1 first, that gives us a value. Now you might have thought of 3 pi halves radians, but again we can't use that one because it's not in the defined interval for angles for inverse sines. We have to use its negative coterminal angle of negative pi halves radians, which we see right there. Now we're doing the cosine of that negative pi halves radians, which is the same as the cosine of 3 pi halves radians, which is 0. And so that is not radians. Now that is actually a value, the cosine value at 3 pi halves radians or negative pi halves radians. A couple more practice problems here. So again, pause your video, do them both, and we'll take a look at the results of both. All right, let's take a look. So here for the first one, we would do cosine of 5 pi 6 first. That is a value. The value is negative root 3 over 2. Then we have arcsine of that. So now we're looking for the angle from, again, negative pi halves to positive pi halves. Sine is negative in the fourth quadrant, so we're looking at this situation. And where sine is negative root 3 over 2, you may have come up with 5 pi thirds, and that is then equivalent to, in this interval, negative pi thirds. For the second one here, we get tangent of pi thirds radians. So we're looking again at a ratio of sine over cosine. So sine of pi thirds over cosine of pi thirds. Sine of pi thirds is root 3 over 2. Cosine is 1/2. And that reduces to the root 3 that we see here. What you need to understand is that the square root of 3 is greater than 1. It's about 1.7. And for cosine, which is now what we're trying to do here, we're trying to find an angle that has a cosine ratio or value of square root of 3, which is about 1.7. And you have to remember that for cosine, the minimum is -1, and your maximum is +1. And so 1.7 is greater than 1. That makes this problem not possible, which is what we see here. All right, so that ends this particular lesson. Have a great day.